Welcome to our lecture online. Our next problem deals with the hydrogen atom and the series, the spectrum of the various series that we can have when an electron jumps from one orbit to another. So let's read the problem. It's very simple. Which of the following statement or statements are correct about the spectrum of the hydrogen atom? So we have four statements. Let's go through each one of them and figure out which are the correct ones. Now let's draw the energy levels. So let's say that here's the lowest energy level, there's the next energy level, there's the next energy level, and the next one, and so forth, like so. And then you realize that for the Lyman series, we have these following jumps, like this. And then for the Balmer series, we'll have these jumps. And then for the Pascan series, we have these jumps, and so forth. Of course, there's more levels, but just to kind of give you a simplistic view of things. And so the first one here says the ratio of the longest wavelength. Of course, the longest wavelength comes from the smallest energy difference, and this would be in the, we're talking about the Balmer series. So we're talking about the Balmer series. So here we have the longest wavelength and the shortest wavelength. And the energy differences, of course, for the wavelength difference here. Let's see here. We have this would be 3.4 electron volts, 3.4 electron volts, and then this one here would be 3.4 minus 1.1. So that would be about that's for the red light. That would be about 2.3 electron volts, I believe. Yeah, something like that. But of course, that's not that important. What we need to figure out is to calculate the ratio of the wavelengths from the shortest to the longest in the Balmer series. So how do we do that? Well, we start with the equation 1 over the wavelength equals the Rydberg constant times 1 over, and then we have what we call n squared for the lower limit minus 1 over n squared for the upper. I shouldn't say limit. I got this reversed here. Square upper. So this is the lowest energy level. That's the highest energy level, and that's then would be the wavelength determined between them. So for the shortest wavelength would be for the least amount of energy difference is jumping from 3 down to 2. So in this case, we have 1 over lambda is equal to r times 1 over the lower limit. That would be 2 squared minus 1 over the upper limit would be 1 over 3 squared. That would be 3 squared, like that. And so that would be equal to r times 1 over 4 minus 1 over 9. The common denominator here is 36. That would be 9 minus 4. That would be equal to r times 5 over 36. Like that. Okay. Now, for the longest jump, of course, you have a whole bunch more levels like that. They get really close together. So at that point, we have 1 over lambda equals r times 1 over 2 squared. That's, again, the lowest energy state, minus 1 over infinity squared, because we're jumping from a very high energy level, essentially infinity. This goes to 0, so we get r times 1 over 4. And then if we convert that to denominator of 36, 4 goes into 36 9 times, so that would be r 9 over 36, like that. Yes. Okay, so now when we want to get the reverse, so in this case that would be, let's call it 1 and 2. So if we then take the reverse, we get lambda 1 is equal to 1 over r times 36 over 5. And let's see here, we want to get the ratio of the longest wavelength to the shortest wavelength. So the longest wavelength will come from the shortest end. This is the longest wavelength. So we divide that by lambda sub 2, which is equal to 1 over r times, that would be 36 over 9. And of course, this cancels out. The 36 cancels out, so it would be 1 and 1. And that becomes 9 over 5. And that is indeed the ratio that we're looking for. We're looking for the ratio of the longest wavelength divided by the shortest wavelength, and so we get 9 over 5, so that is correct. And we probably already used up our 3-minute limit on the problem, but we need to keep going and see what we have. The next one is kind of an easy one to look at because it says there's an overlap between the wavelengths ranges of the Balmer and the Pascan series. So here we have the Balmer series, here we have the Pascan series. Notice that the energy levels range from about 2.3 electron volts to about 3.4 electron volts for the Balmer, and for the Pascan the range goes from like a 1.11 to about 0.54 or something like that. So you know that the energy levels do not overlap, and therefore the wavelengths don't overlap, so you know that B is not a correct answer. And then if we go back to D, it says the wavelengths ranges of Lyman and Balmer series do not overlap. So we look at the Lyman series versus the Balmer series, and again the energy difference are such that for the smallest energy difference is way bigger than the largest energy difference here. So we know that they do not overlap, so that makes this a correct statement when this was a wrong statement. And all we have to go now is look at C. The wavelengths of the Lyman series are given by 1 over m squared lambda sub naught, where lambda sub naught is the shortest wavelength of the Lyman series, and m is an integer. So here we have the Lyman series. This here will give us the jump for the shortest wavelength. That's going from 2 down to 1. And so when we take a look at that, we can say that 1 over lambda is equal to r times 1 over the lower limit, which is 1, minus 1 over 2 squared. So that would be equal to 1 over lambda is equal to r times 1 minus 1 over quarter, which is equal to 3/4 r times 3/4, like that. Okay, which means that lambda is equal to, this is the shortest lambda, right? So we're looking at, given the wavelength Lyman series are given by that, where lambda sub naught is the shortest wavelength. So the shortest wavelength would be equal to 3/4 times r, times 1 over r, because I took the inverse. So when I take the inverse, I get 1 over r times 4/3. So this is the wavelength of the shortest wavelength of the Lyman series. That's when we jump from the second energy level down to the first energy level, and that's what we get here for the shortest wavelength. Now, how about all the other wavelengths? Well, all the other wavelengths are going to be 1 over lambda is equal to r times, again, 1 over 1, because we're going to jump down to the lowest energy level, minus 1 over n squared, or in this case, let's make it m squared, because they use the letter m in our answer. And so we get 1 over lambda is equal to r times 1 minus 1 over m squared. So I look at 1 over 1 plus 1 over m squared. So notice I have a negative here, have a positive there, and lambda, of course, is going to be 1 over r times 4/3. So if you take the inverse of that, we get 1 over, we get lambda is equal to 1 over r times 1 over 1 minus 1 over m squared times the shortest wavelength, which would be 1 over r times 4/3. And you can see that there's no way you're going to get that result, because this is y sub naught, and there's no way you're going to get a plus in there because you have 1 minus 1 over m squared in the denominator. So I would say this one is probably not correct, which means A and D are the only correct answers in this particular case. 3 minutes, that would be very hard pressed. You can quickly figure B and D out. A is not too bad, that doesn't take too long, but the last one here, to figure out that this one is not correct, you kind of have to go through this process, and again, that all takes time, and you'd be hard pressed to get that done in less than 3 minutes. But that is how it's done.